done certain metrics has been about cross-sectional studies, right? So you have certain observations in a society. For example, yi is your dependent variable, and then we said the OLS works like this, where you have equal to some kind of constant. These are all parameters, and you have some kind of xi, for example, maybe x1i, right? So that's your first x, and it's with observation I, and you have some kind of error associated with that I, right? And the problem now is that sometimes we want to do studies. So remember, metrics is all about trying to take certain observations, put it together, and answer certain questions about the population through inference, right? So if you want to ask the question of what the effect is of education on wages, we might want to run a regression and see what that effect is. And we can create inference by doing certain statistics, for example, the t-statistic, on the coefficient on education, and we might interpret it in a certain way. We might interpret it as a causal effect, or we might not, depending how much we believe the various assumptions in the OLS. That's the story so far. So, we might also want to have data which doesn't account for only cross-sections. We might want it to account across time, right? So, examples of this is if something today is caused not by the observation today, but the observation yesterday, right? And so in macroeconomics, this is very popular, and the example we've gone through in class is inflation and unemployment. Inflation might have a relationship with employment yesterday or last year, as well as a relationship with employment this year, right? And in that case, we want to add a certain element to the model. That element being that we want to put a t over here, right? So that each observation is also at a particular moment in time. It's not only a particular person in the cross-section, it's a particular person at a particular moment in time. Right? So the idea is the observation for the same person is not the same as the observation for the same person yesterday. Right? And similarly, the observation of yesterday can be different for different people. Okay? And for this to work, we want to kind of create an analogy with the assumptions of our OS that we've been going through, right? So this is all chapter 10. Was it chapter 10 last week? Yeah. So some of these, so let's look at this example. Inflation T equal to 0 / 1 on soy oil. Q minus 1 / employment Q minus 2. So it can be many periods back. That's error. Okay? So that's the example, one of the examples you do in class. And the idea here is that some of the assumptions still need to hold. One assumption is linearity, right? So that assumption stays the same. The second assumption, no perfect collinearity. It's probably not violated. We usually, in this course, we've never been worried about these two assumptions, right? The third assumption is worrying, right? The third assumption says that the expectation of UT given the entire matrix, right, must equal 0. This is perfectly analogous to the OLS regression, the OLS properties under cross-sectional conditions, right? The mean conditional on your x variables must be 0, but this time your x variables are across all these time periods, and so therefore you have to condition across all of the time periods. That has to be 0, right? And the problem with this assumption is that it rules out, it means that you can have no feedback. right? It's very restrictive. It's a very restrictive assumption. What was the example? So if you look at this example of inflation, how is this violated? How is this property violated in this inflation regression? We went through it last week. So can you think of ways in which the error has some kind of feedback effect with employment? So there was the example of a demand shock in the previous period, right? How can that affect employment? Can there be a relationship between something in the error as well as with the employment? What would that relationship be? So you need to come up with this kind of instance of where this is violated in this model, right? How can this assumption be violated in this model? I'm giving you a hint and saying that if you take the variable within, remember, this error contains countless variables, right? It's everything else that's not in the model. If we take particular, the variable that is demand shocks, right? We can see that demand shock might have a relationship with employment and will have a relationship with inflation, and therefore will bias the estimates, right? What's the kind of relationship we can think of with employment in the previous period? So if you have, for example, if you have less employment now, how will that affect demand tomorrow? People have less wages, and then people have less wages, can they buy as much? No, so demand will decrease, right? So there's a correlation between employment in T minus 1 and your demand shock in T. There's a correlation between employment yesterday and your demand today. There's also a correlation between demand and inflation, of course, right? Is that clear? Is it clear for people back? Yeah? Okay. So that's one example, and you must be able to come up with these examples. Malcolm invariably asks for examples of these things in tests, right? So this is a very restrictive assumption. Another assumption is the variance of UT given X, all X across all periods must be constants. This is like the homoscedasticity assumption, right? Do you remember, can you come up with an example of when that's violated? So the idea was, if it is the case that when unemployment is high, right? So at a particular range of values for X, when unemployment is high, then monetary policy becomes more shaky, right? Because policymakers not sure what to do, or opt for more radical policies, for instance. And monetary policy kind of influences this inflation, right? It means that there's a relationship between employment and the variability of your of your inflation, and therefore the variability of your errors, right? So that will be violated here. Okay. And then the fifth kind of condition is that the correlation between UT and US, given all X, must equal 0, right? And the problem here is that there can be no omitted variable. So whether it's demand shocks or exchange rates or whatever, that affects Y and is persistent. quite easy to think of, right? Because U includes so many different variables, right? It includes everything. And since in the way economic processes work, generally you have a lot of persistence. It means that this assumption is often violated. So for this example, Malcolm uses exchange rates in the error, right? So anything else can be in the error, and he's using exchange rate here. Exchange rate is usually persistent over time. The exchange rate yesterday affects the exchange rate today, right? And exchange rate also affects inflation. So anything that affects inflation and is persistent will result in this condition being violated. Kind of the takeaway of this lecture, that like chapter 10 lecture last week, is that this is too restrictive. Doesn't allow for feedback, and these conditions are very easily violated. So the key kind of thing that you have to be able to do in this regression is that when Malcolm gives you some kind of equation, you're going to have to show how these aspects are violated. So go through those two examples in the slides that he gives. Go through those examples really well. The one example was inflation. There was another example. What was it? I don't know. I don't know. It's in the slides. Okay. What's that? So do you want me to do the chapter 10 problems and then recap chapter 11 and do some chapter 11 problems? Or do you want me to finish the recap and then do all the problems together?
I thought it was chapter 10.
Wait, if there's time, it'll be useful to do some chapter 11 problems as well.
Can you do chapter 10?
We will do chapter 10 problems for sure. But if there's time, we might want to do chapter 10 problems as well. So put up your hand if you want the problems now, or you want the problems now, and the comparison is the summary. So problems now, at 5 people, and who wants the chapter 11 summary now? Wow, people are so indifferent. Oh, I can't tell. It's like some problems now. Okay, this is problem. Okay, so we're not going to do all of the problems. We're just going to do 1, 4, 5, and 6. Okay. So let's look at 1. Let IT and GDP. Does anyone have the? Yeah. I know you have it.
No,
oh, everyone has it.
Yeah.
Okay. So let inflation and GDP denote the short-term interest rate and annual percentage change in GDP respectively. Suppose the relationship between GDP and interest rate may be described by the relation. GDP is related to something interest rate plus interest rate for the previous period. This thing is so terrible. It doesn't help. Ugh. So annoying. Okay, so the equation is GDP is related to something plus the interest rate in period T plus delta 1 interest rate in period T minus 1?
Yeah. No, so delta 0 is t minus 1.
Yeah.
delta 0 is t minus 1. And
Yeah.
then it's t minus 2.
T minus 2.
And then t minus 1 for you. Yeah.
Like that.
Yeah.
Okay.
Because it's t minus 1 for GDP as well.
Oh.
Yeah.
Well, that's a bit useless. What's the
Yeah.
point of doing it that way?
I don't know.
Okay. Well, you can see that this is equal, right? If you just added a 1 to everything, it would be equal to t. This is t minus 1, this is t. Okay, so just make sure you're comfortable with that. No, man, that's not what it looks like.
Oh, that's it.
Yeah. You're misleading me here.
It's different, yeah. Because if you use the textbook, it's the way I see it.
Okay.
Yeah.
Well, this is in the problem set. This is how it looks like. Okay. Okay. So the question A is what is the impact propensity and what is the long run multiplier? It's quite intuitive. What does impact propensity mean? Yeah.
It's the immediate impact of the interest rate on
So the
Contemporary.
the impact propensity is going to be equal to delta 0. And in the long run, propensity is equal to delta 0 plus delta 1. Right? So just in your mind, the long propensity, you just add up all the terms that have an I in it across all periods. And the impact propensity, you just look at the one that's contemporaneous. So you just look at the one that's the same t. Okay? Same time, yeah. Sorry, you have to learn that though because it's often used. Contemporaneous just means the same time. B. Now suppose the Reserve Bank follows the backward looking policy rule. IT is equal to GDP T minus 1. Something complicated. So policy rule IT is equal to, has someone got it? I don't want to shift back and forth.
Is equal to gamma 0.
Oh wait, you gotta print it out? Can I take it from you? Thank you. Gamma 0 plus gamma 1 GDP T minus 1 minus 10 plus VT. Right? So you can see this bit over here looks a lot like that over there. And the question is, VT is uncorrelated with UT and with all past values of IT and UT. Show that even under that condition, IT and UT minus 1 are correlated. Right? So, what you need to do is to kind of substitute things in, right? So first of all, you might want to start by saying, what is this GDP T minus 1 term? Well, it's this thing over here, just a little bit different, right? So let's write this out. IT is equal to gamma 0 plus gamma 1 times by GDP T minus 1. So it's this T minus 1. So it's this over here, and for every T, we must subtract an additional 1. Right? So someone give it to me.
Alpha 0
Alpha 0
plus delta 0 IT minus 1
IT minus 1
plus delta 1 times IT minus 2
IT minus 2
plus UT minus 1
minus 1.
minus 10.
Sorry, guys. And then minus 10.
Yeah.
So that bit over here corresponds to the GDP bit. And then you've got the minus 10, and you've got a plus of VT over there. Okay. the question is, show that IT and UT minus 1 are correlated. Okay. So what do? You can, for example, start with the covariance, IT and UT minus 1. What is, if you find the covariance, what's the relationship between the covariance and the correlation? Yeah. Do you want to say that louder?
Correlation coefficient is covariance divided by the standard deviation of both of those random variables.
Okay, so what she said was that the covariance has a relationship with the correlation, a direct relationship, proportional relationship, and when the covariance is 0, the correlation must also be 0. Okay, so if we can prove that the covariance, and also alternatively, if the covariance is positive, then the correlation also has to be non-zero. So if we can prove that the covariance is non-zero, then we've answered the question and we've proved that there's a correlation. What is this? How do we do this? It's something. What's the covariance formula? I have to get some other people have to talk. Of IT, yeah. So you can put the short kind of thing you did was expected value of IT UT minus 1, and then you do what? You minus what? IT times the expected value of UT minus 1. Okay. But remember, from the OLS assumptions, this expected value of UT minus 1 goes to 0, right? Because we assume for this equation over here, it satisfies the certain assumptions. And so one of those assumptions is that UT in its expected value goes to 0. So we can cross out that, and therefore we can cross out this whole term. And what we're left with, expectation of IT and UT minus 1. But you can see here that at a minimum, if you take IT and you times it by UT minus 1, you're basically taking expected value of all of this over here, and you write it out, times by UT minus 1. But in the assumptions, we already showed, so you don't need to do all the working because it's quite easy to work out. It says that UT minus 1 and VT are uncorrelated. So the expected value of this product is going to be 0. Expected value of this product is also going to be 0 because you can take out the 10, right? And you're left with expected value of UT minus 1. And that is just 0. IT minus 1 is uncorrelated with UT minus 1. It says and these two are all uncorrelated, and so what you're left with is really this gamma 1 times by this UT minus 1 squared, right? And so what you're left with, and remember this is just your variance, is just this positive term. Does that make sense? Because these all return 0 covariance. But this covariance over here, remember times the whole thing into this one, this covariance over here is going to be it with itself, and that is just the variance, and that's positive. So we've proved that the covariance between IT and UT minus 1 is positive, and therefore the correlation is also non-zero, positive. And that violates one of the assumptions, right? So is it strictly exogenous? No. One implication is that the OS estimates biased, or the work in general is unbiased. Okay, is that fine? Let's go to question 4. So these are just like statistical exercises, which aren't fun, but they allow you to link the statistics quite strongly with the economic models. And that can be really hard, but is the most important part of metrics. Because if you can't link the models with reality, then metrics is a bit useless. So it's the hard part, but it's the most important part. Okay. So, number 4. Suppose you have quarterly data on new housing sales, interest rates, and real per capita income. Specify a model for housing sales that accounts for possible trends and seasonality in the variables. Trends and seasonality in the variables. Has someone got an equation that they've come up with? Or write down an equation. I know most of you haven't done it, so right now, it takes like a minute to do. Write down an equation where you account for possible trends and seasonality. What terms do you need to include to account for trends and seasonality? 30 seconds, just write it down. Write something down. Don't not write something down. Otherwise you're not learning. So we've got housing sales, and we want to relate it to interest rates and per capita income. But we also want to account for trends, because housing sales might just increase with time, generally, for example. Inflation might increase with time, generally, as well. Or, interest rates or income. Similarly with seasonality, housing sales might increase and decrease in different seasons. I don't know there's a housing season, but apparently there is. Okay. Let's go for it. So what's our dependent variable? Someone say it to me. Sorry, I don't want to look at just you giving too many answers. What's our dependent variable? This is easy. They're giving it to you. They say relate something to other things. What's our dependent variable? Housing sales, right? So about housing sales is equal to something, right? But we might want to change. Whenever you see sales or income, what do you usually see going with it? Sorry? A log, right? So let's make that a log. And the idea is just because income is usually distributed not normally, so you want to try and get a normal distribution. Okay, and we want to relate that, so always a constant, and we want to relate it to interest rates. So, I don't know, just put an interest rate there. See. We also want to relate it to per capita income. So this is standard, usually log. Now, the important bit of the question: how do we account for trends and seasonality? What parameter? What term do we add? Who said what? Yeah, that's right. Someone said it. Okay, so you have to add a t in here. So 3 times by t. That just accounts for trends. How do you account for seasonality? Dummy variables. So give me an example. So what's my next term over here? I don't want you to answer, sorry. Someone else. Just tell me what to write. How do you account for seasonality? Come on. Yeah, but just tell me what to write. What's the actual dummy variable? What a dummy variable for what?
Each quarter.
For each quarter, okay? So a dummy variable for quarter 1, dummy variable for quarter 2, a dummy variable for quarter 3, and a dummy variable for quarter 4?
No.
No, why not?
Not
Right. Okay, so we stop there.
Wait, what?
We don't add in a dummy variable for quarter 4 because that will result in perfect collinearity to violate some of our assumptions. I feel like you had like a really great explanation and you appreciate it with that. Okay, so that's question 4. Let's see question 5. The decision to invest. I'm re-giving this back to you. I feel bad now. I'll just look right after. Question 5. The decision to invest in research and development and its ultimate payoff in terms of increased productivity involves considerable lags. Right? So we're going to talk about impact propensity again. Everyone has the model. The following model is estimated using annual data. I don't need to write that, okay? What is the impact propensity in the model? Remind me again. Which parameter is in that equation? What's the actual number of impact propensity of research and development on productivity? 0.105. Okay? What's the long run propensity? Someone just tell me how do you calculate the long run propensity? You add all the coefficients together, right? So it's 0,105 plus 0,246 plus 0,327 plus 0,514, and that gives you 1,192. And see, how would you obtain the standard error of the long run propensity? So we have 1, 2, 3, 4. We have 4 propensities, right? So delta 0, delta 1, delta 2, delta 3. How would you put in the model a long run propensity? You want to estimate the long run propensity. What do you have to do? Someone else. What is the long-run propensity? It's the estimate which sums up all the different parameters, right? So if you want that estimate, we can explicitly just sum up all of those parameters when it's still in algebraic form. Yeah?
So long-run propensity also include beta naught?
No.
So just be the one routine.
Well, it's only the ones attached to your lags, yeah. Okay, so we add up and we make it equal to some kind of parameter, let's say theta. And then you put it back in the model, right? How do you, so if the model is y is equal to alpha plus xt plus delta 1, xt minus 1 plus delta 2, xt minus 2 plus delta 3, xt minus 3 plus ut. That's the essential model, right? You now replace the delta 1, so the technique, with something from this equation. So you reorganize it, right? So y is now equal to alpha plus, but instead of delta 0, you put what? Go for it. Which part is? Which part is B and which part is A? Oh, yeah. This whole thing is C. A and B was, so A was the impact propensity, B was the long run kind of.
It's all C.
This is all C, yeah. There's no D. No, this is all C, yeah.
Even A and B verbally.
So this is all C. Okay, so what can we replace delta 0 with if we want to use this equation? Right, so we can just substitute in, we can bring this across and bring that one back. So delta 0 is going to be equal to theta minus delta 1, minus delta 2 minus delta 3. Does everyone see that? And you're then left with the rest of the equation, the rest of the things in the equation, right? 1 plus delta 2 minus 2, etc., etc., right? Then you have to collect the terms. And you get something else. Your new model. So y is now equal to alpha plus, we want to put the focus, each parameter must be attached to a bunch of variables, right? So theta can be by itself, and theta is attached only to xt. If we look at delta 1, what is delta 1 attached to? It's a coefficient of which variables? Well, we've got the delta 1 here, so it's xt minus 1. We've also got a minus delta 1 here, so you have to go xt minus 1 minus xt. You're just factorizing out the delta 1. Xt minus 1 minus xt. Right? Plus delta 2, and you do a similar thing, whatever. Right? And the key here is that when you estimate the model, you need to regress this thing. So you need to generate a new variable, and you calculate the new variable by saying xt minus 1 minus xt. And you regress that. Yeah? Just because that's if you factorize out the delta 1, you're left with a minus xt and then a plus xt minus 1.
Oh, okay.
I mean, but for the coefficients, if you do it the other way around, the minus will just transfer to the delta 1 and it shouldn't be a problem. Yeah. Yeah. Should be fine. And then, after doing that, so you generate a new variable, all of these, and then this parameter over here gives you your long run. What does M stand for? I don't know.
It's a multiplier, but it's the same.
Long run multiplier. Okay. And of course, stator OS gives you standard errors. And so if you estimate that, then you'll have the standard errors. So that answers the last part of C. So remember they're asking, they want to understand what the standard error of your long run effect is, right? And so earlier on, when we did this regression, right, this one over here, we already knew the estimate for the long run propensity or the long run multiplier. You can just add these up, right? But we didn't know the standard error. And so in order to get the standard error, we had to do this fancy long procedure. And so finally, the long run effect was calculated directly by Stator. And when Stator reports certain parameters, it always reports the standard errors with it through the kind of mathematical methods that we've been going through in class. Okay, so let's do a last question on this section and take a break. 7. Provide answers to each of the following. Explain the difference between strict and contemporaneous exogeneity. Someone tell me. What is... Yeah, you know what contemporaneous means. What is contemporaneous exogeneity? Exogeneity, what is this assumption over here? Something like this, right? One of our assumptions, right? So contemporaneous exogeneity, what does that mean? Yeah? In the same time period. So you'd modify this to say it's just u at t conditional on x at t equal to 0. That's contemporaneous. Strict exogeneity. In practice, what does this actually mean? This means that ut is uncorrelated with xt, xt minus 1, xt minus 2, all of those xt's. You can see it's quite different. The one's conditioning on all t's, strict exogeneity. The other one's conditioning just on the same time period, and that's called contemporaneous exogeneity. Okay, let's take a break.